I will begin with a word of prayer. So, here we go. Dear Heavenly Father, I thank you for these students. Thank you for this class. Just pray that you'd help us to use this time wisely, Lord, and to glorify you in what we do here this day, Lord. In your name I pray, Lord Jesus. Amen. So here is the course guide. I printed it out, and so if you want to take one and pass it back, you can do that.
Thank you.
Mm-hmm. So this basically has the day-by-day plan for what I'm hoping to do, which is slightly incorrect. Like, I'm not covering Venn diagrams today too much, although it's not in your homework either. So here, I'm going to start a couple piles in the back too, and you can work forward. How about that? So I'll start it over here, then you guys go to that side. And here you guys go. Uh-huh. All right. So last class, I saw a question in the front. What was your question? You had a question. What was it? Was it?
Yeah. Is homework graded based on completion or like how many we get right?
I think you have more than one attempt on each problem, so like it's graded on correctness, I suppose. There we go. Now the top hat exercises I'll do today, those are basically going to be just graded on completion. There is a right and wrong answer. So if you get right answers, you might get some, a little bit more credit. But like if you just hear and participate, you'll get full credit, if that makes sense. So like, suppose you got everything right. Your participation probably would be more like 55 points rather than 50 points, all right? If you just come here and make an effort, do everything, you should get 50 points. If you come here, answer all the right questions, you might get 55 points or something, okay? So that's my intention. So let me go ahead. Any other questions before I get started? Okay. All right, so just a reminder, I have an office in DeMoss 4382. These are my office hours. You can email me whenever at jcook4. Here's some more recent pictures of my family, not on my webpage. This is my wife, Ginny, my son, Matthew. That's Benjamin, Hannah, Isaac, and Daniel. Isaac, one of his main goals in life is if anytime my wife takes a selfie with somebody, it is Isaac's goal to have one eye. He's going for a one-eye photobomb. That's his specialty. He's getting kind of good at it. And then this is when they went to Mr. Goody's last week without me. Not happy about that. But anyway. So I shortchanged the beauty of math a little bit last time. So let me just spend about 5 minutes on that, and then we'll get into the sets. But so here's some quotes which illustrate math as an art. Paul Dirac, he said, "God used beautiful mathematics in creating the world." Dirac was one of the founders of quantum mechanics. He's a really giant in physics in the last century. Poincare said, "Mathematics is the art of giving the same name to different things." You might appreciate that more after the end of today. And then I had linked, this is Edward Frankel's lecture on Langland's program. And so you guys ever heard of string theory? Show of hands. So string theory is the sort of the forefront of theoretical physics these days. I mean, some people, you can find its detractors, right? I mean, it has been trying to unify things for about 50 years, and it's still more a theory of theories at this point. But the idea of string theory is basically to say everything is made of strings. And from that, you can derive fundamental physics, right? So string theory is a theory of unification. And I was surprised to learn that there's a similar thing in mathematics called Langland's program. Langland's program unifies different parts of mathematics which are seemingly disparate in very non-trivial ways. This is relatively new mathematics. It was, it's only been invented about the last 50 years, and we're still just at the start of it. So, some of the most brilliant and active creative researchers in mathematics are working on this Langlands program. And this video here, which hopefully will work on my computer, hopefully won't be deafening, we'll find out.
I feel a little bit overwhelmed, because to be here.
He's Russian.
And I'm grateful.
So I guess there's no alternative to end my slideshow to get to the video. Here we go. We don't care about his preamble. Let me skip to, here we go. So I think this is a useful quote.
To start with a quote from my compatriot, a great Russian mathematician, who was also a trailblazer in many ways. First woman mathematics professor, the first woman to be an editor of a major mathematics journal, and so on. And she wrote, many people who have never had a chance to know what mathematics is about and think of it as basic arithmetic consider it a dry and fruitless subject. But in fact, it is a field that requires most of all amortization. In Russian, she said fantastic. But I think it's a good, better translation than English.
So I will post these PowerPoints. If you want to watch this whole lecture, you're welcome to. It's like an hour long. But if you watch it, you'll get a very deep sense of what excites mathematicians. And like I told you guys last time, it's not just calculations. It's really something deeper. We're looking for hidden symmetries and beauty which aren't apparent to most people. And so it is very much an art. And the people who get involved in it have great respect for mathematics in the same way that you might have great respect for the Grand Canyon or Carlsbad Caverns if you've ever been to it, right? I mean, if you've been to some of these great natural wonders, you can't help but have a sense of awe. And if you go deeper into mathematics, you have that same feeling, right? Maybe you don't have that feeling adding numbers and calculating fractions and stuff, right? But anyway. So there's my 2 cents on that. Let's go on here. And I do intend to post these PowerPoints for you. I just didn't quite get to it yet. I will. So we're talking about sets today. A set is what? A set is a group or a collection of objects, right? It's called a set. Objects that belong to a set are the elements or members of the set. And we can describe the set in a few different ways, all right? So we could use words. You know what words are, right? Yeah. My little sister has a master's in English from UVA. I went to her graduation ceremony. That was one of the most ridiculous things I've ever been to. They said that the source of all change in the world starts in the thesis projects of master's students in English at UVA. And I asked my sister after this graduation, I was like, do you guys really believe that? And she said, no, that's just what they tell us because we can't get jobs. So, which is kind of funny, but kind of sad. Although my sister has a pretty good job now. She ended up writing like grant proposals for a dean, and then she got like free education credits. Then she got a degree in cybersecurity, and now I'm sure she makes more money than I do. And granted, her English education did serve her well in that regard. But my point is, she used to have some friends. They'd argue about, like, one was mathematically minded, one was English minded, and the English minded one would be like, how do you think? What do you think in? Because what do we say? What do we think in? Do you think in what? Do you think in pictures? Do you think in words? You think in pictures. A lot of people think in words, right? So the mathematically minded guy goes after she's like, what do you think in? He's like, I think in numbers. But, no, I think mostly we think in words. So you know what words are. Roster notation, that's just when we list it. Like this, here's the roster notation. So here's an example. In words, we could let S be the days of the week our class meets, right? Tuesday and Thursday. I'm sorry, if you guys want to meet on Saturday, I will, no, I'm not going to do it. Now here's it in roster notation, Tuesday, Thursday, right? Then there's also set builder notation, which is very silly for this example, it's a day such that, this is read such that, the day is equal to Tuesday or the day is equal to Thursday. That would be set builder notation. The set builder notation becomes more interesting for other examples, okay? Let's go on. Example 2. Suppose D is the set consisting of the days of the week. So what do you got? You got Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. I was like, did I miss Sunday? No, I got it at the start. Okay, good, good, good. I mean, these LUO people, they got the week starting on Tuesday. I don't know what that's all about. I just know it's wrong. The week starts on Sunday. So anyway, and then so, you know, you can use abbreviations. There's the days of the week in roster notation. All right. Okay, so here's some things that might surprise you. And I think we have to unteach people these things. Because I think most people, if you just ask them, is 1, 1, 2, 3, 4 equal to 1, 2, 3, 4? They'd say, no. This thing has 5 things in it. This thing has 4 things in it. They're not equal, right? But our convention in mathematics with sets is that we only allow 1 copy of each distinct element. All right? If you want to have more than 1 copy of each distinct element, there's something else called a multiset. But you guys don't have to worry about that. That's for math majors, all right? So in here, we say that this is equal to that. They have the same elements because even though we've listed it twice, it's like, you know, it's like if you were included twice on a database, it'd be kind of like that. You know, you're really only there once, but there's 2 labels for you or something. So, all right. And also, the other thing about sets is the order of the elements doesn't matter. All right, it's not an ordered list. So like 1, 2, 3, 4 is the same as 4, 3, 2, 1. And you see this last one? I've still got 1, 2, 3, and 4. I just put 2 copies of 4 in the list. All right? These are all the same set. They have the same elements. What do we mean by well-defined? A set is well-defined if its description is unambiguous. So to give you an example of a set which is not well-defined, how about this? The set of all nice cars is not well-defined, right? Since nice is not a precise term. For example, is a Prius a nice car? Show of hands. Who says yes? Oh, wow. So who says it's not a nice car? Wow, I didn't know there's so much hate towards the Prius. I mean, comparatively speaking. It's not like most of you are just undecided, but, you know, sorry. Now I regret not having a Top Hat quiz ready for this so I could document this. But anyway. So does this make sense? Well-defined means, like, the examples up to this point have been well-defined because there's no ambiguity. It's 1, 2, 3, 4. It's the days of the week, right? But if we use something like nice, something that's fuzzy, we don't really have a well-defined set. All right, so a lot of your homework uses these notations, which, to be honest, are not standard, but they're the ones in your book and the ones in your homework, so I'm going to teach them to you. First of all, the natural numbers, the book denotes by this n. And the natural numbers are just 1, 2, 3, 4, 5, and so on. What's the largest natural number? They didn't teach you? It's what? It's 9? No, 10. Anybody know one larger than 10? You could add 1, right? 11. So you take your favorite biggest number, add 1, there's another number past it, right? Natural numbers are unending, they're infinite, right? So that's what this ... means. It means it goes on and on and on and on and on, right? Okay. Now, whole numbers is the set of natural numbers together with 0. Other countries and some other math curriculums would include 0 in the set of natural numbers, but not in here. So whole numbers are starting at 0, all right? Then you got your integers. Integers are whole numbers and their negatives, right? So you get 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. All right. So the set of natural numbers is also called counting numbers. Set of counting numbers, the 3 dots are called an ellipsis, and they indicate the element of the set continue in a manner suggested by the elements that are listed. All right. By the way, these are negative integers, like -4, -3, -2, -1. Those are negative integers. 1, 2, 3, 4 are positive integers. Have I lost any of you? It's okay to be lost. You can ask a question. Is there, if something I say is unclear, or I just say it too fast, or you're offended by some joke I said, I don't know. I don't feel like I've said anything particularly offensive yet. No? Yeah. More numbers. The rational numbers. What are rational numbers? Rational numbers are those, the book defines it as those with repeating decimals. And I would say this, a rational number is a number with an eventually repeating decimal expansion. Like the start of it doesn't have to be repeating. Here's one, 137 over 13. It is 10.53861, 53861, 53861, 53861, 53866. Oh, wait, I missed the 4. 538461, 538461, and this continues and on and on and on ad nauseum. Do you guys remember notation for this? I might use this notation on the test to be less ambiguous. If I could find my markers. Where'd I put my markers? Huh. Interesting. Nope. Nope. No markers? I know I brought them here. Well, it's going to be hard to write on that board without a marker. Well, oh, by the way, keep an eye on the video every once in a while. If that bar is not bouncing, let me know, because I forgot to charge these batteries last night, so we're in the danger zone. But all y'all are here, so what do you care about those other people who can't hear me, right? Do you guys remember the notation for this? Underline. I think usually overline. Is it underline or overline? That's a good question. You did. So he said over, you said under, but what would I got? 137 over 13. What was it? 10 point. What did I say? 4. 5, 3, 8, 4, 6, 1, 5, 3, 8, 4, 6, 1, 5, 3, 8, 4, 6, 1. Okay, so instead of writing that, we could write 5, 3, 8, 4, 6, 1 with a bar over it, just to denote that it's repeating over and over again, right? I don't know if your book uses that notation or not, but it's a good notation to know about. Yeah? All right. So, what are the other kind of numbers? How about the irrational numbers? What are irrational? Now, your text does not use that nice-looking J. It uses some kind of script J. And I'm sorry, I didn't have a chance to hunt down the correct script J thing here to put in the PowerPoint. My bad. So your text, it's got a more kind of like cursive J. Yeah. Hey, come on. I said, oh, off. Yeah. So what is an irrational number? It says it's the set of all non-terminating, non-repeating decimals. For example, pi. Pi is not a rational number. And so the ratio of the circumference to the diameter of a circle, right? 3.1415926535897 excuse me, 7931244751322 0, 6, you know, the rest, right? Oh, that was nonsense. I just, so yeah, I just made that up. See, because no one has it memorized that far, right? So past the point that you show people, you can just make stuff up. But I appreciate the applause. Now, every so often that backfires on me in like a regular class. I once like, you know, I have like 3.14159 pretty much memorized. Past that, I make stuff up. Okay, good. And so I just started making stuff up, and then I had a student be like, no. I was like, whoa. And I'm like, she had a teacher in high school that made them memorize pi to like 10 digits. So I could not fool her. I mean, that high school teacher had too much time on their hands, obviously, but I respect it. Real numbers, it's the set of all rational or irrational numbers. So like real numbers, you also think of it as the real line, right? The continuum. In your other math classes, you may remember minus infinity to infinity. That's the set of real numbers, right? Okay. So now that we have some language, let's get some more examples of sets. So here's a set builder example. This is x. This is read such that x is an element of W, and x is less than or equal to 4. All right. Let me again write on the board a little bit, just to expand on this slide here. I'll write this over here. So we have S equals to, what we do is we put x here such that x is an element of, what was it? W. And what do we have? X is less than or equal to 4, right? So the way this reads, what this means is x is a number. This reads such that. Now did you move the camera? Does it? Such that x is an element of W, and x is less than or equal to 4. This means x less than or equal to 4. So this is a mathematical notation that expresses that sentence symbolically, right? This is the set builder notation. It's just a fancy way of saying we're looking at numbers which are whole numbers, and they're at most 4. Whole numbers start at 0, right? So we've got 0, 1, 2, 3, and 4. That's this set. Okay? So, but this notation, this vertical bar, you just read it as such that. That's all it means. Okay, so it's like the elements of the set are here, and these are the conditions. You can think of it like a club, right? Like this is a club. In order to get into the club, you have to like meet the conditions, right? Like you have to pay the cover charge, you have to be attired appropriately. Wait a minute, you're a Liberty student, what am I talking about? There's no clubbing, right? Okay, good. All the time. I'm going to ignore that. Although I did have a brother who went to Bob Jones, and he had a pair of roommates who regularly went off campus to such places. So, and that was many years ago. Let's see here. All right, example 4. Oh, thank you. Got it. Suppose we have x such that, can you guys see, is this in the way for you?
A little.
Ah. There we go. Is this in the way for you? Okay. So, suppose we have x such that x equals y squared, and y is a, so this funny looking e, that means element of. That means this is a way of saying that y is a member of that set. This n, I defined like a previous slide or two ago as the natural numbers. 1, 2, 3, 4, 5, 6, 7, so forth and so on, right? So what this means is that we're looking at x equals to y squared, where y is equal to 1, 2, 3, 4, 5, so forth, right? So what's 1? So you got 1. I'm sorry, I forgot the square on 1, but can you forgive me? What's 1 squared equal to? 1, yeah. 2 squared? 4. 3 squared? 9. 4 squared? 16, right? Here, let's add an example in class here. How about if I do this? I'm gonna write the set in roster notation to start with, okay? And then I want you to help me figure out what the set builder version of this is. Did you move the camera over? Sorry, I'm making you earn your keep today. Let's see here. How about this? We've got 1, 8, 27, 64, 125. I'll stop there. So what is this? Yep. They're cubed. So you're like, that's 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed. Right. I know there's a lot of you who didn't just see that. That's okay. I used to live with a nice little lady named Miss Matthews when I was an undergraduate. I lived in her upstairs, and she had a son named Dudley. And Dudley rode a Corvette that he complained about because it hurt his back. Sad. Also really annoying when you're a 18 to 20-year-old and don't have a Corvette. But anyway, I remember him coming home. He's like, I was at the bank, and we had this list of numbers. 1, 8, 27, 64, 125. No one could figure out what it was. We're talking about a bank. These are people who work with numbers. They couldn't figure out what this list is. So don't feel bad if you didn't know what those numbers are, right? But anyway, they're cubes. So then in the other notation, like the example, this would be what? X, such that x equals to y cubed, and y is an element of what? What's that? N, right, the natural numbers. So there you go. So you might have some problems in your homework where it starts you with a roster and then it wants you to figure out how to fill in the blanks for the set builder version of it, yeah? Y'all got that? Pictures are taken? All right, cool. By the way, I do not mind you taking pictures of here, as long as they're pictures of what I write, not pictures of me. Let's see here. Did you put it back over here? Okay, cool. In-class exercise number 1. So, the set of levels in DeMoss Hall to which the north elevator travels is A, B, C, D. This is exciting. Who will win? Who will lose? Where's my top hat? Sorry if you didn't do this already. It's too late. Ha ha. Ha ha. I don't really care. I know I care. I care deeply. How do I run this thing? Present? What? No. Dang. Come on. All right, come on. I made these quizzes in advance this time, so I'm hoping they just work. Thank you. All right, you guys see it?
Yes.
Yeah.
I don't know what north elevator is.
That's okay. That's kind of the point.
That's the point?
Yeah, like which is the north elevator? There are 2 elevators. Okay, I'm talking about fair enough. Is it not a well-defined question? A little bit. I'm talking about the main elevators where there's a crowd of people waiting in the morning to get up here from the 8:15 class. That one. That uniquely defines it. There are like 2 other elevators at ends of the building no one knows about. Let me not talk about those. You freshmen shouldn't know. Tick-tock. Are we done? All right. Let me explain this silliness. So, as I understand it, right, it was DeMoss Hall, right, and then there's 460 behind it, right, and then 29 kind of on the other side if you keep going. 29 is a north-south, and just trying to make sure I'm facing the right way. Am I facing 460 right now? I believe I am, right? So I'm pretty sure that's south, and this is north. So that would be the elevator on the left of the 2 in the main, and that's the one that goes to the 5th floor. So this was the answer. However, reasonable answers include just the 1st floor or none at all. As you know, sometimes the elevator does not work. So reasonably, you could have said this, this, or this. And actually, to be fair, some of you would be like, sometimes the 5th floor is locked out. So this is also a reasonable answer. I couldn't disagree. All right, so I promise the next in-class exercise will be slightly more interesting. But have you guys ever been up on the roof? Yeah, it's very exciting. What's that? A? Because the elevator in the main elevator, the one on the left is the north one, and it goes to levels 1 through 5. It actually exits to the roof. Yep. Yep.
Could I argue that your wording says in the Moss Hall and that's on top?
Huh. But there is a covering, like there's a covering, right, up there. So, is it still inside if there's a roof? There's a roof on top of the roof. Isn't it still inside? If you open a window, are you outside? What is an opening in front of a terrace but a large window? How can we make these just? I don't know. All right, I'll stop. This is becoming a silly place. I appreciate these kinds of arguments. Let's see here. Back to the start again. I may eventually learn how to embed things in here. I don't know. All right, so where were we? Moving along. If A and B are sets, all right, and each element of A is also an element of B, then we say A is a subset of B. All right? And we write A, funny looking symbol, B. This is a subset of B. All right? That's notation for it. And by the way, also, the set with no elements is called the empty set or the null set, and it's denoted by this or just brackets with nothing in it. Right? I use that as the answer to D in my silly poll I just gave you. So here's an example. If we have the set containing A, B, and C, all right, what are subsets of that set? Well, the empty set is a subset of any set because the empty set has no elements, so it automatically satisfies the condition of the set, whatever it is, because there's nothing to check. So the empty set is automatically a subset. The set just containing A, the set just containing B, the set just containing C, these are also subsets of A, B, C. Or you could have just A and B, or just A and C, or just B and C. These are also subsets. And of course, the whole set, A, B, and C, is also a subset of the set. So, I think in the sort of common English usage of the term set, you might reject the empty set and the whole set as being subsets, right? Because sometimes when we use just usual English, conversation, you might implicitly assume that you're looking at what's called a non-empty proper subset. In other words, that you're not allowing for this or for that. But technically, the empty set and the whole set are subsets, according to the mathematical definition. I think I've told you guys this already, but I should mention it again. In math, we don't have a conversation and invent our own truth. In math, there are definitions. And those definitions define what is true. That true is the same for me as it is for you. Math is decidedly not postmodern, right? There is the truth. There is not the truth that you decide. Yeah? There's the truth that whoever writes down the definition decides. Then we all have to work with it. But anyway, so here's a theorem. Any set is a subset of itself. The empty set is a subset of any set. Come on. Moreover, if the set A contains n distinct elements, then A has 2 to the n distinct subsets. Well, that's kind of interesting. Is that true for our example? What would n be here? N is 1, 2, 3. Right? There are 3 elements in this set. How many subsets are there? 1, 2, 3, 4, 5, 6, 7, 8. What is 2 to the power 3? 8. Okay, so if you had a set with 4 elements, how many subsets would you have? 2 to the 4, which is 16, right? If you had a set with 5 elements, you'd have 2 to the 5, which is what? 32, right? If you had a set with 6 elements, you'd have 2 to the 6, which is 64. If you had 7, you'd have 128. If you had 8, you'd have 256. If you had 9, you'd have 512. If you had 10, you'd have 1020. You get the idea. So you have a calculator, though. You don't have to just memorize powers of 2, right? Although you do have a formula sheet. Maybe that would be a worthwhile thing to write on your formula sheet, right? 2 to the 3 is 8. 2 to the 4 equals 16. 2 to the 5 equals, that could be handy on the test. In-class exercise 2. Suppose a pizza restaurant allows you to put the following toppings on a cheese pizza: pickles, pepperoni, sausage, meatballs, pineapple, anchovies, gummy bears, celery, ham, or bacon. How many possible pizzas can be made? I presuppose that cheese is on this pizza. There are those of you who eat pizza without cheese in here. I reject that. That's not pizza. That's like a cracker with tomato sauce or something. I don't know. It's not pizza. Sorry if you're cheese intolerant. Cheese haters. Oh, top hat, yes. Let me top hat you. Is it assigned? I think I had to, there, I clicked the other assign. Is it working now? So this one's got a mathematical input. You got to put the number you think. Just take your best guess if you don't. All right, I'll give you about a half more minute. Make your guess. Just make a guess if you don't know. 44% of you have answered something. Just put something in there. I will explain once we're done with this, but missing 20 more people to go. 81, 82. How many people in here don't have top hat right now? How many people have top hat like not working for some annoying one? Just one? Two? Oh, I see in the back. 2. 3. All right, has everybody answered who can answer? All right. How do I? Oh. So here we go. Here's the answer. So the way to think about this is that the number of pizzas, right, corresponds to the number of distinct sets of toppings. Right? So if you think about that, you've got 10 toppings. That's a set with 10 things. So the question is, how many subsets are there of a 10 topping set? Well, the theorem we just went over says that there are 2 to the 10 subsets. Right? Now that includes what? The empty subset and the whole subset. So we were including on the one side of the one, on one side nothing, just a plain cheese pizza. That would be the empty set, right? Or you could have a pizza with pickles, pepperoni, sausage, meatballs, pineapple, anchovies, gummy bears, celery, ham, and bacon, which would be kind of disgusting, I think. But yeah, so that's why there are 1,024 possible pizzas. So there's a problem or two like this in your homework, so I thought I should work one like this in class with you. Yep.
I got it right, but actually, if you were including the empty set, wouldn't that be 2 to the 11th if there's 10 different toppings?
No, because this includes the empty set. Like there's 2, so in the set with ABC, the empty set was one of those 8, right? That would be analogous to the no toppings.
Right.
Yep. Where does the 2 come from and the 2 to the power n? Oh, well, so now you're asking me to derive the theorem. I don't know if I can do that in here. I think the right answer is, I'd have to give a proof by what's called mathematical induction. I'd assume the theorem is true for n, and then I'd show that that implies it's true for n plus 1. I'm not sure if I know a good, off the top of my head, like heuristic reason, which is what you'd rather hear me say. But it's a good question. I'm not sure how to answer it at the level of this course. That's a very good question. All right, so moving on here. So, next up, so by the way, I'm covering sections 2.1 and 2.2 in the book, not quite in the order the things are listed. I just took everything in 2.1 and 2.2 and jumbled them up and put them in an order which made sense to me to talk to you guys about it in the time we have. If you read the book, the order of the discussion is a little bit different than my order. Okay? Just saying. So, this lecture is sections 2.1 and 2.2, all right? Which is what your homework, which is due Saturdays on. Now, if U is the universal set, universal set, that's kind of funny. as I read it. And A is a subset of U, then the complement of A is the set of all elements in U which are not elements of A. So we denote the complement of A by A prime, all right? A prime. Now, you may have had like another course where you used A bar. Like I usually use A with a bar over it, but your book uses A prime, so I'll do that. A prime, and that's X, such that X is in the universe of elements, the universal set, and X is not an element of A. This means this element with a slash through it, that means not an element. All right? Now, here's a theorem. If U is the universal set, then the complement of the universal set is the empty set, and the complement of the empty set is the universal set. So what are the set of all, what are the set of all elements which are not in the universal set? Well, that's, if everything's in the universal set, what's not in the universal set? Nothing, right? So that's the empty set. On the other hand, what's not in the empty set? Well, everything. So the complement of the empty set is the universal set. Here's an example. If the universe we're looking at is numbers, counting numbers 1 through 10, right? And my subset is even counting numbers from 1 to 10, right? 2, 4, 6, 8, 10. What's the complement of it? In other words, it's the numbers which are not even and in the universe of discussion, right? So you could call it the universal set. You could call it the universe of discussion. You could just call it the universe. U is for universe, okay? And so it is everything that's not these, right? Which is 1, 3, 5, 7, and 9. So that's the complement. Here's another one. If U is the set of real numbers and Q is the set of rational numbers, then the complement of the rational numbers, that's X, such that X is a real number and X is not a rational number. All right? That's actually another way to define the set of irrational numbers. See, because either a real number has a repeating decimal expansion or it doesn't. If it doesn't, it's an irrational number, right? So we can define the irrational numbers as the complement of the rational numbers. It's unfortunate that rational and irrational sound so similar when we're talking. It would be great if we called the irrational numbers like zucchini numbers or something. I don't know, just something that sounded totally different than rational. Or just call them the crazy numbers or something. I mean, oh, I'm sorry, insensitive. Whatever. If I double down on that comment, it's just going to make it worse. So let me go on. Any questions about this? The number of elements in a set S is known as the size, or fancy math word, cardinality. So cardinality is a fancy math word for size, the number of elements in the set, all right? So we denote the cardinality of S by n of S, and when S has a finite number of elements. Now, what do I mean finite number of elements? I mean, if you had enough fingers, you could count your fingers to get to it, right? You might need a crowd to get enough fingers, but if you had enough people with enough fingers, you could count it, right? So, on the other hand, there are sets we've talked about today which are not finite, right? Natural numbers are not finite. How many natural numbers are there? They go on and on forever, right? So that's an infinite set. The integers, an infinite set. The real numbers, an infinite set. Pretty much all my number systems were infinite sets. Most of our examples have been finite sets, right? I could write a list which begins and ends, and it had what, like no more than 10 elements for the examples we've looked at today, right? All of our examples pretty much have been finite sets. With the exception of the one I did over here, like this was an infinite set, right? Because it went on and on. Or the set of squares, it kept going, right? Those were infinite sets. All right, but if it's finite, then we say n of s is the actual number of elements. Otherwise, n of s denotes what's called the cardinality of s. Let me tell you a little bit more. If a set A and a set B have the same number of elements, if they have the same size, if they have the same cardinality, then we say A is equivalent to B. And we write this for A is equivalent to B. So A squiggle B, right? They're equivalent. On the other hand, if the sets A and B have the same elements, right? The exact same elements, then we say that A and B are the same set, and we write A equals B. All right, let me try to show you the difference between equivalent and equal. So if we have the set A is Bob, Jane, and Naruto, and B is 1, 1, 2, 3, how many elements, come on, how many elements are in A? What's the number, what's the size of A? 1, 2, 3, right? The number of A is 3. What's the number of B? If you're thinking it's 4, what have you forgot? We do what? We throw out duplicates, right? So there's really just 3 numbers in here because the number 1 is just a double. So we just keep one of those. This is really the same. B is equal to 1, 2, 3 here, all right? So B also has 3 elements. So A and B here are equivalent because they both have 3 elements. Are they equal? Are they the same? They are not, right? Because Bob is not 1, Jane is not the number 2, and Naruto is not the number 3. Are you with me? You're like, what's this Naruto you're talking about? You some sort of nerd or something? It is true. You caught me. Let's see here. What am I talking about? There's nothing cooler than liking Naruto. It's an epic story full of beautiful music and artistry. And it helps you understand the importance of acknowledging people and the danger of not acknowledging people and what comes from that. There's deep truth in Naruto, despite its ancestor worship. All right, anyway. Ancestor worship bad, for the record. Right, okay. Example 9. Let A be a toaster and a doorknob. Okay. And let B be boss, chief, and throat wobbler mangrove. All right. It's an exceedingly silly name. So how many things are there in A? 2? How many things in B? 3? Are these equal? Nope. A toaster is not a boss or a chief or a throat wobbler mangrove, and neither is a doorknob. These are clearly different. They're not equal, and they're not equivalent either, right? Because one has 2 and one has 3. They're not equivalent sets. Show of hands, who knows what I'm referencing with throat wobbler mangrove? Ah, okay. Ah, someone can Google. Yeah, I know. I know how it is. That was too long. See, Google has ruined all conversation, right? Well, I mean, in some sense, but okay, so Cantor is a famous 19th century mathematician who did deep work in the theory of sets, all right? And he studied the size of sets very deeply, all right? He was a brilliant mathematician. His work was very controversial for its time. I don't think he was really, I'm not sure, I can't remember, you know, a lot of times people who do really deep work, it's only really recognized once they're dead. That happens a lot, especially back in the 19th century and before. But anyway, Cantor, he had this theorem. One of his theorems was this: the size of the power set of a set A is strictly larger than the size of A itself. So what's the power set of a set? The power set of a set, this is a little bit meta, and not like that. He's ruined that word, that robot. So the power set of A is the set of subsets of A. So like if you take my example on a couple slides back and put a set around it. So back here, this right here, if you put a curly bracket here and a curly bracket here, then this would be the power set of ABC. It is a set of sets. And what Cantor proved is that the set of sets of a given set has a larger size than the set itself. This is obvious for a finite set, right? But Cantor proved it for infinite sets as well. That starts to blow your mind a little bit, right? How do you judge the size of an infinite set? Do you guys have an idea? So here's some infinite sets, right? Well, here's some infinite sets. How do you judge the size of an infinite set? I'll tell you what it is before I assign this, all right? So you judge the size of an infinite set by comparing one infinite set to another, all right? So we could say that if there's a one-to-one correspondence, right? So what's a one-to-one correspondence? It means like you can take this one set and you can draw a line from that set to the other set, and like from each element of the set you can just draw a single string to the other set you're mapping to, like that, and then the next element goes to another thing, and you can just keep mapping each element in the first set to the second set, and there's a string connecting pairs of elements for every possible pair of elements in one set and the other. If you can do that, if you can make a one-to-one correspondence, they're said to have the same size, the same cardinality. So that's what's meant when I ask the question, do these sets, how do you compare the cardinalities of these sets? All right? Let's see if you can, let's see what people think, all right? Let's see what people think. Ready, set, go. You have a minute. So you have two choices, all right? It closed? Why would it close? What? It's good? Okay, good. I think my computer's on the internet, so it should work. Hey, wait a minute. I want to show you that. Look away! Probably not good form to show you the answer while you're taking the quiz, right? By the way, I think this current quiz, I don't think your homework really covers this. This is more, I want you to understand a little bit about. So we have, and just to remind you, natural numbers are this, right? Whole numbers, integers, rational numbers. How did the cardinalities of these compare? I need to bring like a stopwatch.